Welcome to the presentation of the paper on fast and space-efficient construction of AVL grammars from the LZ77 Parsing. My name is Dominik Kempa and this is a joint work with Ben Langmead. One of the main motivations for this work is the problem of efficient computation of run-length compressed Burrows-Willard transform, or RLBWT. The input for this problem is a massive, highly repetitive text which is typically given as a file or a collection of files on disk. The output of the problem is a file containing run-length compressed Burrows-Willard transform of the input. For the purpose of this talk, we only need to know that the output file is a compressed representation of the input text, and in many applications it is orders of magnitude smaller than the input. Construction of RLBWT is one of the central problems in the field of compressed indexing, which is concerned with the design and construction of data structures that enable searching or even running complex algorithms directly on compressed data. Compressed indexing finds applications in many domains. This includes, for example, storage and searching of source code repositories like Git, which contain many versions of the same file, handling versioned documents such as Wikipedia, or performing the analysis of massive pangenomic DNA databases. The standard approach to the construction of run-length BWT is to construct it directly from the text in a single step. Assuming the input text is of length n, the construction usually takes linear or near-linear time. Moreover, there exist algorithms whose working space is roughly O of r, where r is the size of the output, that is, the run-length compressed BWT of text. In our example, assuming each symbol of text takes a single byte, the value of n is 75 times 10 to the 12, and the value of r is 5 times 10 to 9. In this paper, we focus on a different approach to the construction of RLBWT that was proposed recently. The main idea is, rather than performing the computation of BWT directly from text, to instead split the computation into three steps. The first step compresses the input text using the LZ77 compression algorithm. As shown in that paper, the output of the first step is provably close to the size of run-length compressed BWT. Thus, for highly repetitive input, already at this step we achieve a reduction in space by orders of magnitude. The second step converts the LZ77 compressed text into a grammar compressed text. The size of the resulting encoding is also provably close to the size of run-length compressed BWT. Finally, in the third step, we use the grammar augmented with some indexing data structures to obtain the run-length compressed BWT. The motivation for performing the computation in this way is that this simplifies the most expensive step of the algorithm, that is, the one taking linear time. The intuition for why computing, or more precisely approximating the LZ77 compression is easier, is that it only needs to find some repetitions in the string without considering the order between all suffixes, which is needed in the direct approach to the construction of run-length BWT. The key property of this three-step algorithm is that once we obtain the initial LZ77 compression of the input, the remaining steps of the computation will be significantly faster, since they only take time proportional to the size of compressed data. Let us take a closer look at the three-step algorithm. The first step converts the input text into its LZ77 representation. It is the only step that requires linear time in the length of the text, and hence it is both of importance that this step is fast and use little working space. The crucial property that lets us achieve this goal is that the rest of the algorithm works correctly even if the output is an approximation, or in other words, some small LZ77-like representation of the text. Some fast algorithms for this problem have been proposed recently. In this paper, we use the algorithm by Kosolobov et al. The second step of the algorithm takes the LZ77-like representation of the text and converts it into a context-free grammar. This problem is solved by the classical algorithm of Rytter. Despite good theoretical bounds on its size, the basic implementation of this algorithm produces a grammar that is many times larger than some of the best grammar compressors. Furthermore, to the best of our knowledge, no highly optimized implementation of Rytter's algorithm is available. The third step of the pipeline is the conversion from the grammar representation into the run-length compressed BWT. Since this algorithm is very recent, no implementation is available. We note, however, that its space usage largely depends on how big is the input grammar. Given this situation, in this paper we focus on the earliest step of the pipeline that does not have efficient implementation, that is, on the second step, converting the LZ77 parsing to a grammar encoding. Our contribution is a series of space-reducing techniques that significantly lower both the working space of the algorithm as well as the size of the final grammar of Rytter's algorithm. We have also implemented the proposed algorithm and experimentally compare its performance to the existing elements of the pipeline, as well as one of the fastest algorithms that constructs the output RLBWT directly from the text. Let us formally define LZ77 compression. The key concept in LZ77 is the longest previous factor, or LPF. The LPF of I is the longest substring starting at position I that has another occurrence starting at some position j smaller than I. In the example, the LPF at position I has length 4. The LZ77 compression is then defined as follows. Given a string t of length n, we greedily, that is, left to right, partition the string t into LPFs, or single symbols if the LPF has length 0, and then output the encoding of each LPF, or single symbol, as a pair. By z of t, we denote the number of pairs in the output. Suppose we have already partitioned this example string up to position 11. At this point, we take the LPF at position I, which in this case is a substring of length 3 starting at position I with an earlier occurrence at position 7. We then encode it in the output as a pair of integers containing the length and the position of an earlier occurrence. Thus, we next look at position 15. In this case, the LPF at position 15 has length 5 and an example earlier occurrence starts at position 5. We thus append the pair 5, 5 to the output. This concludes the compression algorithm. The value of z of t for this string is 7, as the output consists of 7 pairs. Let us now look at grammar compression. Let us first quickly recall some basic definitions. A context-free grammar G is defined by a set of variables v, a set of terminals sigma, and a rule set R. For every rule, which is a pair A alpha, where A is a variable and alpha is any string of variables and terminals, we say that a variable A expands to string alpha. The language of grammar G is then the set of strings over the alphabet of terminals that can be derived from some fixed variable S. The idea of grammar compression is, given a string t, to find a context-free grammar G such that G has the smallest size, assuming that we measure the size as the total length of expansions in the rule set, and the language of G is precisely the input string t. Here we see an example grammar whose language is the string t equal to ABAAB. The size of this grammar is 6, which is not optimal because the trivial grammar containing a single variable expanding to the whole string is of size 5, and thus achieves a better compression. In general, however, the trivial grammar will not be optimal. To the right we see a so-called parse tree of this grammar. It is simply a complete derivation tree of the grammar such that it has the variable s in the root, and all the leaves are terminal symbols. Thus, when we read the symbols in the leaves from left to right, we obtain the string t. The basic idea of Rytter's algorithm is based on the so-called AVL grammars, which were introduced in that paper. A context-free grammar is called an AVL grammar if its parse tree satisfies the AVL property, which means that for any non-terminal n expanding to x and y, the height of the parse tree for x differs from the height of the parse tree for y by at most 1. An immediate consequence of this is that heights of parse trees for all non-terminals in the grammar are O of log n. The conversion algorithm works as follows. We process all phrases one by one from left to right. The algorithm maintains the invariant that after the first k phrases have been processed, it has an AVL grammar expanding to the concatenation of these k phrases. To maintain this invariant, we proceed as follows. We take the next phrase and let the green rectangle be the substring of the text corresponding to the source of this phrase. We decompose the source substring into a logarithmic number of non-terminals such that the concatenation of their expansions is equal to the substring. To do this, it suffices to perform 2 traversals in the parse tree. We then use the classical algorithm to merge AVL trees, suitably modified to work for AVL grammars. To merge all these non-terminals into a single non-terminal, we will use the resulting non-terminal to represent the currently processed phrase. We then again perform the standard concatenation of AVL trees, this time for the grammar of the first k phrases and the just created non-terminal expanding to the current phrase. This restores the invariant of having the grammar expanding to the first k+1 phrases. To analyze this algorithm, Rytter has proved that the sequence of non-terminals that is being merged in the second step is bitonic, and moreover, when we perform the merge of non-terminals from short to tall, the number of extra non-terminals introduced in the whole process is only logarithmic in the length of the string. This proves that the whole process takes only O of z log n time, and that the resulting grammar has size O of z log n. In this work, we propose the following practical optimizations to Rytter's algorithm. The first improvement is a delayed merging of non-terminals. The main idea is to change the main invariant, requiring that after processing the first k phrases, we have an AVL grammar expanding to their concatenation. We instead allow for the currently processed prefix of the text to be the concatenation of several non-terminals. To ensure that the number of these non-terminals do not grow very large, we employ the rule that we only merge them whenever they are entirely inside the source of one of the phrases. Let us look at the example assuming the following source substring. We first decompose it into some number of non-terminals. Note that this number may be larger than logarithmic. Note also that to perform such decomposition, we take all non-terminals that are entirely inside the source plus the non-terminals obtained from the decomposition of 2 boundary non-terminals. We then merge the non-terminals of the main sequence which are entirely in the source substring. And finally, copy over the resulting sequence to represent the new phrase. Note that the number of these non-terminals is logarithmic in the length of the string. We implemented this improvement and observed that it very significantly reduces the number of extra non-terminals which are introduced in the algorithm, but never used in the final grammar. One last detail is about merging of non-terminals which are entirely in the source substring. Rather than merging them left to right, we use the intuition from Rytter's algorithm that choosing the non-terminal with the smallest height leads to small number of extra non-terminals. Thus, our merging is a greedy algorithm that always chooses the smallest remaining non-terminal and merges it with the shorter neighbor. Our second technique for reducing the number of extra non-terminals utilizes Karp-Rabin hashing. During the algorithm, we maintain the collection of Karp-Rabin hashes for some subset of non-terminals. As a practical optimization, we can control the fraction of non-terminals which are hashed. This does not affect the correctness of the algorithm. Then, whenever we append the sequence of new non-terminals at the end of the current root sequence, we perform a quick dynamic programming algorithm that uses Karp-Rabin hashes to try and reduce the size of the appended sequence by finding a shorter sequence of non-terminals with the same expansion. Note that since Karp-Rabin hashing works correctly only with high probability, this turns our algorithm into a Monte Carlo algorithm. We note, however, that this optimization is easy to turn off, leaving us still with a very efficient algorithm. The analysis of this optimized algorithm does not change significantly compared to the basic algorithm. The only major change is that our procedure to merge the non-terminals enclosed in the source substring needs a priority queue. This adds another log factor to the time complexity. In our first experiment, we compared the size of the grammar produced by our optimized algorithm with the basic implementation of Rytter's algorithm. We also compare it to Rytter, which is a grammar compression algorithm that is one of the best in terms of the size of the output grammar. In comparison, we also include the size of the grammar obtained by running basic Rytter's algorithm and then removing all non-terminals not reachable from the root. The figure shows the comparison of the sizes of grammars produced by all 4 algorithms on the files from the pizza and chili corpus. All files are normalized with respect to the size of LZ77 parsing. Our new algorithm produces grammars that are only between 1.59 times and 2.64 times larger than Rytter. The resulting grammar is always at least 5 times smaller than produced by the basic Rytter's algorithm, and also always smaller than its pruned version. Importantly, the RAM usage of our conversion is proportional to the size of the final grammar, whereas the algorithm to compute the pruned version must first obtain the initial large grammar and then perform the pruning. This increases the peak RAM usage very significantly. In our second experiment, we evaluate the potential of the three-step RLBWT construction, which works by first approximating the LZ77 parsing of the input, and then converts the parsing into a grammar and finally the run-length BWT. In the comparison, we include three algorithms. First, the algorithm of Kosolobov et al. To show the performance of LZ77 approximation. Second, we include our optimized implementation of Rytter's algorithm. Finally, we include the algorithm of Boucher et al., which is currently one of the fastest algorithms to construct run-length compressed BWT for large, highly repetitive strings. We evaluated the runtime and peak RAM usage of all three algorithms on successively longer prefixes of two large test files, whose statistics are displayed on the bottom left. Both files are highly repetitive, with the average LZ77 phrase length on the order of thousands. The graphs on the left show the peak RAM usage of the algorithms measured in GB bytes. We note that the algorithm of Kosolobov et al. Is a full external memory algorithm, allowing us to specify the RAM usage arbitrarily. We set its RAM use to match the RAM use of big BWT on the shortest prefix we tried. Our algorithm achieves a very low RAM usage compared to big BWT, which confirms the effectiveness of our optimizations. It also scales very well as the file becomes larger and more repetitive. Let us now look at the runtime visible in the graphs on the right. The runtime of the LZ77 approximation algorithm is always below that of big BWT, which confirms our hypothesis that approximating LZ77 can be done faster than computing RLBWT directly. The reduction is by a factor of at least 3 for all prefixes of the test file used on the bottom plot, and by at least 25% for all prefixes of the other test file. On the other hand, the runtime of our optimized implementation of Rytter's algorithm stays significantly below that of both other methods. Given these results, we conclude that the construction of RLBWT via LZ parsing has the potential to achieve at least a threefold speedup and a similar reduction in the RAM usage. This concludes the presentation of our experiments. Future work includes the design and implementation of fast algorithms to approximate the LZ77 parsing. In particular, exploring the trade-off between the speed of computation and the approximation ratio may lead to even faster algorithms. Another important avenue for future work is designing algorithms for scalable models of computation, such as parallel and distributed models. Finally, we propose to explore methods that are based on hashing. These methods will not always provide a correct output, but may lead to very fast approximation algorithms and with some care may achieve a very low probability of error. The second important problem for future work is completing the pipeline by implementing the conversion from the grammar into the run-length BWT. On the way to this result, we first need to achieve fast construction of data structures for the longest common extension queries. Another intermediate component is the efficient implementation and fast construction algorithms for grammar-based indexes. We also need the implementation of compressed string synchronizing sets, as well as the run-length compressed wavelet trees for long strings. This concludes the presentation. Thank you for listening.